Yes, and Seiberg-Witten monopoles. Well, actually, I asked the organizers what could be an interesting topic for this workshop, and that was a suggestion of the organizers. But it makes the talk necessarily somewhat a survey talk, because there is a lot to say, and probably I won't have enough time for the proofs. Because there is also one more object that I need to talk about. These are Fueter sections that live in between G2-instantons and Seiberg-Witten monopoles. So let me start with those objects. So Fueter in 1934 tried to generalize complex analysis to the quaternionic setting, and what he came up with is the following version in 3 dimensions. So you consider a map U from R3 into quaternions, and you require that they satisfy so that U satisfies the following equation. So you take du over dx1 multiply by I, and du over dx2 multiplied by j, and the same with du over dx3, and this is 0. So I will call such maps Fueter maps. Now there are several observations in place. So first of all, this makes sense for any base manifold. So let us concentrate on 3 manifolds. Namely, if you choose a spin structure, then this equation will become the equation for the harmonic speed. All right, so maybe let us know this F. And also, one more remark is that this also makes sense for arbitrary target spaces, as long as the target space has 3 complex structures, I, J, and K, so that they satisfy the quaternionic relations. So this also makes sense for hypercomplex X with complex structures I, J, and K. So in fact, we will be interested here in hyperkähler manifolds, but you know what you need is also only 3 almost complex structures. So hyperkähler manifolds often arise as hyperkähler reductions, and you may ask, can we describe Fueter maps when the target is a hyperkähler reduction? So the setup is as follows. So you assume that X is a hyperkähler reduction of some, say, quaternion Hermitian vector space. So where T is and you view this as a flat hyperkähler manifold. You also assume that there is an action of a Lie group G on V, and this action is 3 Hamiltonian. That is, you have a hyperkähler moment map from V into the Lie algebra of G. So I identify the Lie algebra of G with its dual taken 3 times, and I can write this as a map into G tensors with imaginary quaternions. And what you do, so then this X is nothing else but the 0 level set of mu divided by G. And the basic result in this story is due to is an older result of myself. So assume 0 is a regular value of mu, and G acts freely on the 0 level set of mu, then there exists a bijection between the space of Fueter maps and the space of solutions, so the space of pairs A psi, where these satisfy the following equation. So you take the covariant derivative of psi with respect to the first variable, and A here is a connection. I will write this just in a moment, and multiply by I j plus k. So this is 0, and mu of psi is 0. So you take all solutions and divide this by gauge transformations. All right, so maybe I will also tell you what is psi here. So psi is a map from R3 into V, and what stays here is a nabla. So A is a connection on the trivial, on the product G bundle, and what you have there is a covariant derivative. You don't need to assume here that your base manifold is R3. You can do this for an arbitrary manifold, but then you have to talk about certain sections of certain bundles, and I want to avoid this at this moment. All right. Now, so the correspondence here is very easy to describe, and also the proof is not hard. What you have is, you know that psi maps you R3 into the 0 level set of mu, and so here you have a projection onto X. So what you do, you just take the projection of psi and you know this for U, and it turns out that U is Fueter if and only if this equation is satisfied. All right, that's how you get those equations. Now, you get A. So this is, by our assumption, this is a principal G bundle, and actually it is equipped with a natural connection because you have a metric here. So you declare your connection by orthogonal complement, and what you do, you just take the pullback. All right, so let me move now to G2-instantons. So the setup is as follows. So you start with a 7 manifold. This is equipped with a Riemannian metric G and a G2 structure phi. So and phi is a 3 form on Y, and I denote by psi the corresponding 4 form. And you fix a principal G bundle over Y. Well, let me stick here maybe to SUN bundles. And then a connection A on T is called a G2-instanton if what you do, you take the curvature of A, you multiply this with So we take the wedge product with psi, and you require that this is 0. So this equation just is to say that a certain component of the curvature vanishes. And what you should think of this equation as a nonlinear elliptic PDE. You should be quite careful with the ellipticity, because it's not straightforward from this expression. You have to there is a way to embed this into an elliptic complex, and you can proceed in the usual way as in the gauge theory, but with some care. Anyway, so this equation is to some extent very similar, or has some similarities with flat connections on stream manifolds. Just to give you an analogy. And now the basic result is due to Tian, roughly in 2001. Let AK be an arbitrary sequence of G2-instantons. So actually, Tian proved his theorem in a much more general context, but I will stick to G2-instantons only. Then there exists a subset M in Y and a subsequence which I will still denote by AK, converging over the complement of M. Moreover, the dimension of M is at most 3, and if the dimension of M equals 3, then M is associative. Well, this means that if you pull back your associative 3 form to M, what you get is a volume form with respect to the induced metric on M. I'm not terribly precise here in the theorem. There are still additional issues to be considered. So for instance, this M may have another component which has something to do with irreducible singularities. I'm completely ignoring this. So so I would rather write this as there is a set which is a union of two subsets, and I'm assuming the set here is 0. All right. Yes, I do. Yeah. Yes. Well, you don't need to assume holonomy G2. I think what you need only to assume that phi is closed at this point. Phi. Yes. All right, and in the proof, what Taubes actually constructs the following. So you have your ambient 7 manifold Y, and in here you have a 3-dimensional subset M. So it has the normal bundle, and the normal fiber here is R4. And the way Tian proves that the tangent spaces here has this property. So he shows that on each normal space you have an ASD instanton. So let me write this. So for each point M in M, there exists a non-trivial ASD instanton on the normal fiber to M, which is R4. And what this means is the following. So we can construct a bundle M over M, and this is a bundle obtained by replacing each fiber and M, so which is just R4, by the moduli space of anti-self-dual instantons on NM. So maybe by the framed moduli space. And so what you know very well is that this is a hyperkähler manifold. And so for sections of this vector bundle, the Fueter condition makes sense. Well, so first of all, there is a section I of this bundle, and the conjecture is that this section is actually Fueter. It's not very hard to understand why the section must be Fueter. So at the end of the day, this comes down to the theorem that I have presented to you. So what you do, so in a small neighborhood of your associative submanifold, you can think about this subset as a total space of the spinor bundle over M. And on the spinor bundle, you can write your G2-instanton equations as an analog of Seiberg-Witten equations. So as these equations with an infinite dimensional target space. And sort of formally, you reduce in certain limit to Fueter condition. Anyway, so I would like to skip this at this point and maybe proceed further. So. The following result by Valpusky suggests that this is maybe not a bad conjecture. So if I is a generic, in a certain sense, Fueter section, then I can be deformed to a family of G2-instantons. This means the following. So if you have a Fueter section, you can find a sequence or a family of G2-instantons in a small neighborhood of M, which develops a bubble along this submanifold M, and in the limit, what you see your original Fueter section. Now, an observation is that the virtual dimension of the space of Fueter sections. So is 0. I mean, this is an obvious fact coming from the fact that we have an elliptic system of equations and we are on an odd-dimensional manifold, so the index is always 0, and we have therefore virtual dimension 0. But on the other hand, if you have one Fueter section, you'll always have a one-parameter family of such sections. This is because the moduli space of anti-self-dual instantons has an action of real numbers by dilations. Right, so and if you dilate an instanton, so if you have a Fueter section and you dilate this, you still have a Fueter section. This follows easily from the equations, and this means the following. So this means that a one parameter family of G2 a one parameter family of matrix on M, there are finitely many matrix admitting a Fueter section. So in other words, you expect Fueter sections to appear in codimension 1. And in turn, what this implies is the following. So if you take a family of matrix now on your 7-dimensional manifold M, say parameterized by 0 and 1, so for a generic value of t, you expect to have finitely many G2-instantons. But if you vary t, what can happen is that one of the instantons will develop a bubble. So at this point, you will see an associative submanifold or a current together with some Fueter section, and afterwards this disappears. Right? May happen several times. Some may survive, and some may be born by a symmetric process. So, and the conclusion is that the number of G2-instantons may jump in one parameter families of G2 matrix. Now, so it is clear from the picture that this behavior because of this jumping behavior, you can't define an invariant of G2 manifold just by counting G2-instantons. Right? We have started with 3 points and we ended with 2 points, and this is obviously not what you want to have. So the question is, how do you correct this behavior? And here, this is where the Seiberg-Witten theory comes into play. Okay, so let's now move to the Seiberg-Witten equations. So for this, you don't need to have any G2 structure, so you just start with an arbitrary closed oriented and Riemannian 3-manifold. Such a manifold is always spin, so we can choose the spin or bundle of M. And what we can, so this bundle is has a very nice property that the space of skew-Hermitian endomorphisms of S can be identified with the cotangent bundle of M. And so if I multiply this by I, I can identify my Hermitian endomorphism of S with imaginary valued one forms. And then we also choose Hermitian line bundle. And a connection on L. So A is a Hermitian connection on L. And we consider the following equations, which I will call Seiberg-Witten equations with n spinors. So what you do, you require that the spinor is harmonic and the curvature couples to some quadratic term in the spinor. Now, so this looks pretty much the same as the Seiberg-Witten equations that you know, but what is what here? So psi here is a section of the spin C spinor bundle. So this is my way to write a spin C spinor bundle, but taking n times. So instead of just one spinor, I consider the n tuple of spinors. And what is mu? So mu of psi is what I can do, I can write, as I said, psi as an n tuple, say psi 1, psi n, and then mu of psi is just the sum psi j star minus 1/2 norm of psi j squared. So each individual term here appearing in the sum is the usual quadratic map appearing in the Seiberg-Witten theory, and what we do is just sum up all those terms applied to individual spinor. All right, so and these are Seiberg-Witten equations with n spinors. Now, what maybe what you see here in the sum is a Hermitian endomorphism of the spinor bundle. This follows just from the expression, right? But we know that Hermitian endomorphism can be identified with the imaginary valued one forms, and this is precisely what stays on the left-hand side of the equation, right? So this match here precisely. Yeah. You know, that depends how do you think about connections on line bundles. You can think of them as real valued one forms, and you can think as imaginary valued one forms. I'm thinking here as imaginary valued one forms. Okay, and this is sort of the standard procedure in the gauge theory. Once you have some gauge theory, the first question you would ask is a moduli space compact? Right, we know very well that if you have just one spinor, the moduli space is compact, and that's why you can define the Seiberg-Witten invariant essentially. But for this generalization, is it true? So it turns out it is true, but with an extra constraint, namely the space a psi, so that we have a solution of the Seiberg-Witten equation with n spinors, but you impose the condition that the norm of psi in L2 is bounded by some constant. So maybe for any C, the space of solutions modulo gauge transformations is compact. And the proof here is essentially just the repetition of the proof in the classical Seiberg-Witten theory. So that's quite an easy proposition. But now you see, I put it there a constraint which which is quite unnatural. So it may happen that we have a sequence in which the norm of spinors goes to infinity. So what happens in that case? So assume that we have a sequence, say ak psi k. So is the sequence of solutions of SWN such that the norm of the L2 norm of the spinor goes to infinity. Well, you can't get anything convergent in this case because we just go to infinity, but what you can do, you can rescale your spinor to get any chance for the convergence, and that's what I will do. So I'll denote by psi k twiddle to be 1 over lambda k psi k. And so what does this satisfy? Well, the first equation can be renormalized easily because it's linear in psi, right? So I can just put twiddle here. But the second equation can't be that easily renormalized because the second, the term on the right-hand side is quadratic, right? And this means that instead of this equation, if I want to put twiddle here, I have to compensate this by putting lambda k to the power minus 2. And now, if you pass formally to the limit, when lambda k goes to infinity, what this will do, this will kill us this term, right? And I end up with the following equation. So dA psi infinity twiddle is 0, and mu of psi twiddle infinity is 0. But now these equations have a very familiar form, namely these are equations that I have started with. They are not already on the blackboard. So this describes us Fueter sections in certain hyperkähler reduction. Right, so let us figure out what is this hyperkähler reduction. So what I do, I start with V to be C2, say tensored with Cn, and here I have an action of U1. So the action of U1 is given, say, by just multiplication on one of the components. So meaning that if you represent the space as C to the power 2n, it acts diagonally on each component. And then if you compute the moment map of this action, so this space is obviously hyperhermitian, and mu of psi 1 psi n turns out to be precisely what you have here in this equation, that is psi j dual minus 1/2 norm of psi j squared. So and by the theorem that I have presented to you,
here you're assuming that the charge is equal to 1 for all of the something.
I think that's what I said. So they are acting right just by multiplication, say power 1 on each component. Is that? And so if I denote this equation, say by 2 stars, then 2 stars describe us Fueter, well, in this case sections, because we have started with the general 3 manifold. What is important, these are with values scheme, what we do, we take the hyperkähler quotient of V by U1, and by the ADHM construction, this is M1N. So with a circle there, and what this means, that this is the space of framed, centered charge 1. So this one stays for charge 1, SUN ASD instantons over R4. Say it again? Yeah, so this space, you know, the moduli space of framed, centered, charge 1, this one stays for charge, SUN instantons, so anti-self-dual instantons over R4. Right, this is just a particular case of the ADHM construction, which gives you descriptions of the moduli space of anti-self-dual instantons over R4 as a hyperkähler reduction. All right, so, but now, what does this mean? This means the following. So, if you have a family of matrix on your 3-manifold M, so for a generic matrix, there are no Fueter sections with values in this space, just by the same reason why there is no Fueter sections in the G2 case. Right, so you would expect that you have some finite number of the Seiberg-Witten monopoles, maybe one here. But now, if you vary your metric, what can happen is that one of these solutions develops, so goes to infinity, right? And at this point, so for this particular metric, we see a Fueter section over M. And so what can happen is also a reverse process in which from a Fueter section you would get a family of Seiberg-Witten monopoles. Right, so now the idea is that we can put those two pictures on top of each other. That is what I can do. So I'll just write the same picture over here. Well, so what does this mean? This means the following. So instead of counting just G2 instantons, let us count pairs. Namely, we start with G2 instantons, and for this particular metric on your ambient G2 manifold, we have some number of associatives, and we count Seiberg-Witten monopoles on associatives. Right now, we vary the metric on our ambient G2 manifolds is various metric on associatives, and associatives also flow. But what happens in the process? At some point, you see that a G2 instanton converges to a Fueter section. And then this Fueter section will give you a burst to a Seiberg-Witten monopole on your associative. Right, and you can see this in the other direction. So you may have a Seiberg-Witten monopole which converges to a Fueter section. This may then go into a G2 manifold, into a G2 instanton. And if you do this, so conjecturally, if you started with 4 points, you ended with 4 points. But here, the points change from G2 instantons to Seiberg-Witten monopoles. So all this is conjectural. Right, so just what can be proved is more or less if you have a Fueter section on an associative. So Thomas's result tells us we can go in this direction, right? And we have a variant of this direction. So let me present this. So the theorems that we proved together with Thomas Walpurski roughly a year ago. So let AK psi k be any sequence of solutions of the Seiberg-Witten equations with n spinors with lambda k, so the norm, the L2 norm of the spinor tending to infinity, then there is a closed subset Z in M, and a subsequence still denoted, well, maybe by the same index, but in this case we have AK and the renormalized spinor converging to some limit A psi, and this converges over the complement of Z. Now, what can be said about the data appearing in this theorem is the following. So A psi solves these equations. So this is precisely what we expect to have, except that the solution is over the complement of this subset Z. Now, the norm of psi, so the pointwise norm of psi extends as a continuous function to the all of M, and that is the zero locus of this function. And what we can also say is that Z is nowhere dense. In particular, Z is not the whole manifold M, in which case the statement is empty. Okay, so one remark here is that this result, as well as the proof, is very closely related to the work of Taubes on flat PSL2C connections. Well, in fact, so we just borrowed his idea and his methods of proof, and so essentially what he did in the case of flat PSL2C connections, we did for the Seiberg-Witten equations. Now, you see, so we expected to get we don't have the convergence over the whole manifold M, but just on the part of the manifold M. So on the complement of the subset Z, and you would wonder what can be said about Z except that this is nowhere dense. So there are a few results about that, namely theorem due to Taubes roughly in 2014 says that the dimension of Z, so the Hausdorff dimension of Z, is at most 1, and that contains an everywhere and maybe an open open, everywhere dense subset, which is a Lipschitz submanifold of M. So to a certain extent, that looks like a one-dimensional object, right? So and a very recent result of myself actually is again a manifestation of this one-dimensional behavior of Z. Namely, so if you assume that we have just two spinors, then so let me formulate very roughly. The homology class of Z is the Poincare dual of the first-chain class of L squared. So you should understand L squared as the determinant line bundle of our background data, and then it has a well-defined Poincare dual class. So you may ask, what is the statement? The statement is that Z has a so there is an extra structure on Z which makes this homology class to be well defined, and this is equal to this homology class. So this is in H1 and Z. Now maybe I will tell you which problems do you have to deal with. First of all, that is not smooth. So maybe a remark before that this is valid for all metrics on M. So there is no restriction on the metric on M, no assumption about genericity or whatever. Now, if you have sort of an arbitrary metric on M, what can happen is that Z is not smooth, so you shouldn't understand this homology class as a homology class of a subset or submanifold. And then even if Z is smooth, Z doesn't need to be oriented. So you have to find a way to put an orientation on Z, and then even if you have this, what can happen is that you have to count components with certain multiplicities. So what can happen is the following. So assume for some choice of matrix you have Z as these two curves, but then you may vary your metric, and in some limit what you will get, you get just one circle which is oriented like this, and this should be counted this way too. Right, or else what could happen is also this. So you have two circles which are oppositely oriented, so you vary your metric, and in certain limit what you see just one circle, but these circles sort of cancel each other. Geometrically you see a subset here, but you should count this with weight 0. Right, and once you have done all of that, you can prove that this homology class is well defined. It just depends on the subset Z and some extra data, and this equality holds. So there is an analog of this theorem for all n, but in the case when n equals to 2, so in the case when we have just two spinors, I don't need any extra assumptions, whereas for the higher number of spinors, I need some extra assumptions to to get this result. Anyway, let me stop here. Thank you very much. So, one thing that I have forgotten to say, maybe I should have said this at the beginning, is all this is joint work with Thomas Walpusky. So.
You've explained how to get this Z from the three manifold pictures, suppose I follow one of these white curves out into a purple curve. Would that Z be empty or not?
It's not very clear at this moment. So when we have started this project, we didn't know that there is some extra set Z there. But my current guess is that you indeed have to see the Z also in the G2 picture.
This information is missing from the conclusions of Tian still. I mean, it doesn't produce this extra structure.
Right, right.
So one can say more.
I mean, so this Fueter section that I told you about is not in the Tian's paper. This is already sort of a refinement of his work. But pretty much probably is that it must be still refined further.
And I guess that's giving more information even than telling you what the determinant line bundle needs to be once you've produced the Fueter section.
Right. Right. So I don't have a clear picture how this works with this extra data with the Z, but this is yet to be worked out.
Can you say anything about the curvature of this limiting connection A in your theorem? It seems to disappear by the scaling process.
No, it didn't disappear completely. I just didn't need, for this exposition. So what you can say is that if you have just two spinors, then in the limit you have a flat connection over the complement of Z. In general, what you do, you will have some line bundle over the Grassmannian, and the limiting connection is a pullback of this sort of universal connection.
The behavior of the limiting A, psi near the singular set Z, is that somehow under control, or?
It is under control to a certain extent. Namely, what you have is well. What you have, so you have your manifold M and you have Z in here. Z is of co-dimension 2. And what you know is that the holonomy of the limiting connection A is contained in plus minus 1. And so if you square this, you will have a connection on the determinant line bundle with a trivial holonomy, right? And this gives you a section over the complement of Z of the determinant line bundle. And now you can ask, but Z is a one-dimensional object, so you can trivialize your determinant line bundle over Z, and this gives you two trivialization on the neighborhood of Z. And so there is a transition function, and you may ask what is the degree of this transition function, because it's just a map, sort of when restricted to a small circle. You have a map from a circle to a circle, and so you may ask what is the degree of that, and the degree turns out to be precisely the multiplicity function which I mentioned here. So this gives you in some sense control over the limiting connection, but at the moment that's all what I can say.